We're going to begin our next topic of study by using a graphic organizer. If we were in class, I would have given you some colored paper, encourage you to fold it, and create these four spaces. Now, the topic is going to be simplifying radicals. You can certainly put that in the middle, but we're going to use the front and the back to study simplifying radicals with two specific rules. Now, the first rule is going to be called the product rule. And you're going to find out that the product rule is actually something we've kind of been playing around with through various problems, but now specifically we're going to introduce to you that the product rule says that if I'm trying to do the nth root of AB, that would be the same thing as trying to do the nth root of A times the nth root of B. Now, you may be even wondering, well, what does it mean to do a root? And we're going to go back through that, but a root is the idea of trying to break down a number, according to the type of root. Maybe it's a square root, maybe it's a cube root. But I just want you to focus on this rule with me one more time, because it is actually kind of a simple rule that really just says that if I'm trying to do the nth root of a product A and B, that would be the same as splitting it up into each individual root, the nth root of A, the nth root of B. Now, before we get any further in this lesson, just like we would be doing in class, make sure that that you're thinking. There's going to be times for you to actually try some problems. If you haven't folded a piece of paper yet, or you're not ready with your notes, make sure you pause the video. As this concept, it would be challenging whether we were in class or not. This is typically a harder idea for students. I'm going to walk you through it carefully, but you want to be ready to go here. You want to be ready to think, to process this, and like I said, even to try some of these problems on your own. So when you're ready, advance the video, and we're going to get started here in the upper left corner, where we're going to take a look at numbers. All right, so let's start by considering simplifying some radicals that involve numbers. Now, if we wanted to simplify the square root of 8, as we've actually talked before, that would be like thinking or trying to find a perfect number that's inside of 8. Now, when we talk about a perfect number, we're talking about like a perfect square root. That would be the number 4, because 4 times 2 equals 8. Now, the product rule says that I can actually split this into the square root of 4 and the square root of 2. But as we've actually already talked a few times this year, that's what we mean by trying to take out this perfect number. Because when we take out this perfect number and think of the square root of 4, well, we get the number 2. So we're left with 2 root 2. Now, do you feel like you recognize this kind of problem? You should. We've talked about it before. And of course, it involved thinking about a square root. But what if I wanted to do like a different kind of root? And that's what a lot of this chapter is going to be about. What if I wanted to do a problem that, for example, was maybe like 16 to the 1/3 power? Now, you might first be saying, what? How am I supposed to even think of 16 1/3 power? Remember from your last video that that this is like a flower. You think of this as like a flower, where the number in the top is the power and the number in the bottom is the root. And so really 16 to the 1/3 power is the same as trying to do the third root of 16. Now, how do I do the third root of 16? How do I simplify that? Well, much like we did the square root of 8, you try to find a perfect number inside of 16. But you see, you don't want to think of the number 4, because the number 4 is not a perfect number when it comes to thinking of a third root. You see, you want to be thinking of numbers that are perfect cubes. Now, it might be helpful to make a list of numbers that are perfect cubes before we go any further, because those are the kind of numbers that we want to find inside of 16. So what are some perfect cubes? Well, 1 cubed is 1. What's 2 cubed? 2 cubed is like 2 times 2 times 2. That would be 8. How about 3 cubed? 3 cubed is 3 times 3 times 3. Well, that would be 27. Next would be 4 cubed. 4 cubed is 64. 5 cubed? Well, 5 cubed would be 5 times 5 times 5. Now, should you be memorizing these numbers? Well, I would say you should be able to access these numbers. You should be able to find them on a calculator. And I'm not going to make you guys work with numbers that are real big, but it is helpful to also know that 6 cubed, which is 6 times 6 times 6, is 216. So again, you don't have to memorize these numbers, but you want to have access to them. And in this case, when we go back up to our problem here, trying to find a perfect number inside of 16, a perfect number that's inside of 16 would be the number 8. Specifically, we can think of 16 as 8 times 2. But again, the number 8 is the number that's perfect, that's inside of 16. Now, at this point, I can use the product rule. I can split this problem up. I can split it up to be the cube root of 8 times the cube root of 2. Or I can think of just taking out this 8. Either way, when you do it, you have to understand that the cube root of 8 is going to come out to be the number 2. And that leaves us with the other 2 still under the radical. So we end up with what's known as 2, the cube root of 2. Let me write that a little bit better. It comes out to be 2, the cube root of 2. Let's try another one. As I said, I know that this is new and this can be challenging, but you can do it. You're just going to have to focus and try, and we will be here to help you along the way. Now, this is the cube root of 54. Okay, the cube root of 54. Well, to simplify this, we want to try to find a perfect number that's inside of 54. But again, it's a cube root, so we want to be thinking of perfect cubes. Okay, you go up to your list, you ask yourself, is there an 8 inside of 54? Well, I don't know. Is there an 8? You'd have to divide it by 8. It doesn't divide by 8. Is there a 27 inside of 54? Well, it turns out that there is. So I can split this problem up to be as if I'm thinking of this as 27 times 2. Now, of course, 27 times 2 is still equal to 54, but now I have my perfect number. And you can take out your perfect number, and when you take it out, it turns into its root. Now, remember, the cube root of 27 would be which number that I can multiply together 3 times to get 27. And of course, that would be the number 3. Now, that is also where this 27 came from. It came from 3 times 3 times 3. Now, notice that you still leave behind this 2. So this 2 is still under the cube root. So we're left with an answer known as 3, the cube root of 2. All right, so now's an opportunity to try one of these. See if you can do the cube root of 32. And then if you want to try to do the square root of 96, again, we're trying to simplify, so we're finding a perfect number that's inside of each of these expressions. Push pause on the video, try the problem, and then when you play the video again, I will be explaining it. I encourage you to try it, though, before you watch me explain it. All right, so to do the cube root of 32, we're trying to find a perfect number inside of 32. Now, it has to be a perfect cube number. From our list of cubes, we have 1, 8, 27. There's other numbers also. There is an 8 inside of 32. The reason there's an 8 inside of 32 is because 8 times 4 is equal to 32. Okay, as long as I can multiply, or really as long as I can divide it evenly, then that number is in there. Now, the cube root of 8, as we've seen a couple times, is able to come out perfectly. It comes out as a 2, and it leaves behind the 4. So we're left with the cube root of 4, and when you say the final answer, you would say 2, the cube root of 4. Now, for the square root of 96, you want to be thinking of perfect squares. We actually haven't made that list, but you've been thinking about those kinds of numbers for quite some time. But it never hurts to think of them again. Perfect squares would be like 1, 4, 9, 16. Now, notice that all these numbers come from squaring an integer. And so if I square 5, I get 25. Square 6, you get 36. You get the idea. You've seen these numbers before. The question really is, which one of these numbers is inside of 96? Now, you always want to get as high as you can. So if you start dividing, you'll discover that 4 divides into 96. 4 is an interesting number, though, because it might be also the case that 16 can divide. And in this particular problem, that is true. So since it's a square root problem, we're going to break this into 16 times 6. Now, the product rule says that I can split this if I want. You might notice that I haven't done that for the last few problems because really this step is more of just something you think about in your head. What you really can do is you can just take out the perfect number. Of course, when you do the square root of 16, you get 4. And really, that leaves us with a final answer of 4 root 6. Now, this was a square root. It was a square root, so I had to think of perfect square numbers. But if it's a cube root, I have to think of perfect cube numbers. Well, what are you going to do if maybe it's like a 4th root? Can we do a 4th root problem? Well, sure. We just have to think of a perfect 4th root. Now, 4th roots... those would be numbers that came from multiplying together 4 times. So like 1 times 1 times 1 times 1. How about 2 times 2 times 2 times 2? That comes out to be 16. How about 3 to the 4th power? 3 to the 4th power, that would be like 3 times 3 times 3 times 3. Well, now that jumps up all the way to be 81. So there are perfect fourths. Actually have a little bit of a typo here. It's not a 4th root, but it's really more of a 4th power. But the real question is, which one of these numbers is inside of 32? And it turns out that there's a 16 inside of 32. Now, 16 times 2 is how I can break up 32, but I'm going to be able to take this 16 out. Now, when I take it out, I want to be thinking of its 4th root. So it's going to bounce all the way back down to the number 2, because that's where the 16 came from. And it leaves behind the 2 that was underneath. And we would read this answer as 2, the 4th root of 2. Now next, we're going to talk about the product rule with variables. So if you did organize your paper, we can move over here to this upper right corner, where we're going to look at how to simplify radicals that involve variables. Now, let's see what maybe we already know. Let's see what we can add. Okay, now this would be an example of a radical that has a variable. We would call this the square root of a to the 3rd. Now, you actually learned in the last video that this would be the same. This could be turned into a problem written with a rational exponent, where the numerator is the power and the denominator is the root. There's nothing wrong with what I did here, but the truth is I didn't really simplify it. I just kind of changed its form. If we want to try to simplify this, what we really want to do is we want to try to get smaller numbers. So let's revisit this square root of a to the 3rd, and let me help you think about how you can find a perfect number inside of a to the 3rd. Now, what do I mean a perfect number? Well, I'd be talking about a perfect square, and it turns out that a squared is inside of a to the 3rd. If I was going to think of this as a squared, I'd have to also then think of a times a, because of course a squared times a is equal to a to the 3rd. But you see, now that I split it up into a perfect square, I'm able to actually do the square root of a squared. And the nice thing is that the square root of a squared simplifies to just be a. Now, the square root of that a that was left behind does not simplify. But I have turned this into smaller numbers. We would read this answer as a root a. What if I wanted to do the cube root of maybe something like b to the 14th? Well, I'd have to try to think of splitting up b to the 14th into some perfect cubes. It turns out that there's a lot of perfect cubes inside of b to the 14th, because if you break down the number 14 into separate b to the thirds, you would be able to end up with 4 of them. You see b to the third, b to the third, b to the third, b to the third, and a leftover b squared. They all would equal and go back to b to the 14th. So why would I want to split this into all these separate b to the thirds? Well, because each of these b to the thirds has a perfect cube root. You see, I could take each of these out, and every time I do the cube root of b to the third, I'm going to be left with a b. Well, how many b's are we going to be left with? Of course, 4 b's, because each one of these comes out, and as they come out, they reduce down to just be b. Now, it's important to realize that this b squared is left behind, and it's important to realize that all of those b's that are in front of this equation really just equal b to the 4th. Take a look at this final answer. Let me write it a little bit nicer. It's b to the 4th, the cube root of b squared. Now, there's a shortcut to this, and the shortcut is understanding that each of these circled b to the thirds, each of these circled b to the thirds, is really just the same as a b to the 12th. And b to the 12th is a special number because it divides evenly. Okay, it divides evenly with this 3 out front. So if you would like, you can think of your b to the 14th as b to the 12th times a b squared. And the reason I want to use the number 12 is because that's the highest amount of b's that are inside of 14. Now, what happens with this 3 and this 12 that I circled out here? What happens with this 3 and this 12? Well, they simplify by dividing. And when you divide them, you end up with b to the 4th. And you're left with just the cube root of b squared. Same answer that we got up here. In order to simplify that radical. Let's try another one. This would be the square root of x to the 7th, y to the 4th. Now, yes, it is a square root, so since it's a square root, we assume that there's a 2 here. And the nice thing about that 2 is it becomes the number I want to think when I try to find perfect numbers inside of x to the 7th. In other words, I want to find the highest number inside of 7 that's going to divide with that 2. And the highest number inside of 7 that divides with that 2 would be 6. Now, I also have to think of a regular x so that I end up adding everything up to still be x to the 7th. How about y to the 4th? Do you realize that y to the 4th is already a perfect number? In fact, all of those 4s are going to divide nicely with this 2. And this is exactly what happens. All you have to do is take out your 6, but when you take out your 6, it's going to divide with that 2. It's going to leave me with an x to the 3rd. It also leaves behind this x that's underneath because that x is not perfect. How about this y to the 4th? When you take out that y to the 4th, you're going to divide it. And it divides with the 2. In fact, all of it divides and leaves us with just the y squared. So our simplified answer would be x to the 3rd, y squared, root x. I'd like you to try one. I know that this is challenging, but you can try to find how many 5s are inside of x to the 9th, y to the 14th. How many how many 5s are inside of each of these numbers? And then can you pull that out? This would be a good time to push pause, try the problem, and then I will show you the answer in the next step. All right, so when thinking about splitting up x to the ninth, you want to find the highest number that divides with 5. And in fact, that only can be 5. It's also important that you realize that it leaves behind x to the fourth. That's the amount that is not perfect. How about this y to the 14th? Did you think of it as y to the 10th and y to the 4th? Okay, because 10 is the highest number that divides evenly with this 5. So when you take out x to the 5th, when you take it out, it's going to divide with the 5. And it leaves us with just x, or x to the 1st. When you take out this y to the 10th, it's going to divide with this 5. And that leaves us with y squared. Now, those that did not come out are left behind. And we end up with x to the 4th, y to the 4th still under the square root. So our final answer is x, y squared, root x to the 4th, y to the 4th. Would you like to see an extra problem? See if you can break out a to the 10th and b to the 12th. Now this is the 4th root. Okay, so you're trying to find the highest number inside of 10 that divides evenly with a 4. You should be thinking of a to the 8th. Now that does leave behind a to the 2. You also want to be thinking of the highest number inside of 12 that divides by 4. Well, the whole thing divides evenly. So we can take out a to the 8th. When you take it out, it divides and leaves us with a2. You can also take out all of this b12. That's because all of it divides, and it leaves you with b3. Now, what's left behind is just this a squared, but it's really the 4th root of a squared. Okay, I know these problems are kind of tricky, but we have a squared, b third, and then the 4th root of a squared. Next, we're going to take a look at using this product rule, I guess you could say backwards, but really not backwards. It's more just starting with 2 radicals and trying to turn it into 1. So we're going to be in the lower left corner of your graphic organizer, taking a look at the product rule in reverse. All right, so how about a lovely problem like this? The square root of 12x to the 6 times the square root of 3x to the 4th. Now what we have here are 2 radicals that are being multiplied together. And the product rule says that I can take 2 items and I can pull them together to be 1, which again is the reverse of taking 1 and splitting them to be 2. Now, when we do this, we just got to do some good math. 12 times 3, of course, that comes out to be 36. And we also want to figure out how to multiply x to the 6 and x to the 4th. Now, remember, when you multiply, you always add the exponents. Of course, that's the atom property that my son was named after. So when you multiply, you add the exponents. Well, of course, that's going to give us x to the 10th power. Now, this wouldn't be our final answer because as we've been talking, we might be able then to pull out some perfect numbers. And since this is a square root, we just want to be thinking about if we can pull anything out of 36. Well, 36 itself is already a perfect number. And so I can do the square root of 36, and that will come out to be 6. But how about this 10? Are there any perfect, what's the largest number inside of 10 that can be divided by this 2 out front? Well, the whole thing can be divided. So we actually take this whole x to 10, and we can pull that out. Of course, when we pull it out, the 10 gets divided by that 2, and we end up with 5. So our final answer is going to be 6x to the 5th. Think you can do this? Let's try another one. Let's try the cube root of 4x squared times the cube root of 4x to the 5th. Okay, now again, we have 2 radicals, and the product rule says that we can take 2 and we can pull them together to be 1. Now, to pull them together, all we got to do is multiply. So, of course, you're going to multiply 4 and 4. That's pretty easy. That's going to give you 16. And you're going to multiply x squared and x to the 5th, but that really means you're going to add the exponents. So we add them, and we get x to the 7th. Now, you always want to be thinking, is there something inside of these numbers that that we can take out? In other words, is there a perfect number inside of 16? And when you're thinking of perfect numbers, you want to be thinking of perfect cubes. Well, you should encounter the number 8. Now, it's 8 times 2, but it's really the 8 that we want to be thinking about because we're going to take that out. How about x to the 7th? Now, when you're thinking of variables, you want to think of the highest number inside of 7 that's divisible by this 3 out front. And you should be concluding that that would be a 6. Now, there's also an x left over because I want to end up with x to the 7th. So we're going to take out our 8. We're going to do the cube root of 8. The cube root of 8 goes all the way back to 2. We're going to take out this x to the 6, but that means we're actually going to divide it by 3. We're going to divide it by this 3 that's out front. So when we divide the 6 by 3, we end up with x to the 2nd. And then left behind, my cube root left behind would be the 2 and the plain x. So we end up with 2x squared, the cube root of 2x. I want you to try one of these on your own. The square root of 6x times the square root of 3x to the 6. Push pause, and then meet me back here for the worked out solution. All right, so the product rule says that I can take two roots, two radicals, and I can pull them together to be 1. Just multiply 6 times 3 and get 18, and multiply your x's. Of course, you're going to add the exponents. Now, the square root of 18x to the 7th, maybe there's some perfect numbers inside of here. And in fact, there are. You certainly can think of 18 as 9 times 2, 9, of course, being your magic perfect number. And you can think of the largest amount of x's that can divide evenly with this x to the 7. Excuse me, with this 2 out front. So that'll get you the whole way up to x to the 6 and only leave you behind a single x. So both these circled items are able to pull out, and when they come out, they get smaller. So we take out the 9, that comes out as a 3. We divide the x to the 6, and that comes out as x to the 3rd. Left behind are the 2 and the x, so we end up with 3x cubed, the square root of 2x. All right, so we have one more category to look at. It's actually going to be what I'm just going to call a special category. It's not necessarily especially hard. It's just got a little different look to it. But you're going to have to click on the next video, part 2, in order to finish out this last category.